Hello, I'm Regina, and welcome to my Physics 2211 Lab 4. Today we're going to be talking about oscillation. So, before we get started, I'm gonna go over what we're going to go over today. First, we're gonna go over the introduction, where we're going to discuss the purpose, the fundamental concepts, and the experiment summary. Then, we're gonna go over our experiment, then our model with our math and our code, and then finally, we're going to move on to the conclusion, where we're going to talk about our reflections and our follow up questions. Our purpose for this experiment is going to be to analyze the motion of an oscillating object. We also want to explore the law of energy conservation as well as how it relates to Newton's second law. And finally, we also want to compare the predicted motion of our object and the observed motion of the mass. Some fundamental concepts that we want to go over for this experiment include Newton's second law, which states that the acceleration of an object is dependent upon two variables, the net force acting upon the object and the mass of the object. We also want to learn about the law of conservation of energy, which says that the energy is neither created or destroyed. Energy changes from one form of energy into another form of energy. It is also important to consider that in this case, in this lab, our net forces involve gravity and the spring forces. Here are some relevant formulas that we might need. This includes kinetic energy, a spring potential energy, and gravitational potential energy. The methodology for our experiment summary includes comparing the predicted motion and the observed motion of the mass in both the x and y directions, and also plotting the energy changes that you compute in the model, aka the change in kinetic energy, the change in gravitational potential energy, the change in spring potential energy, and the change in total energy. So for the first part of our experiment, we made use of tracker. In this video, you can see how we plotted each position of our oscillation over time. It is also important to note that in this case, our system is the mass and the spring and the surroundings are the air. On the right side of the video, you can also see the plot of the mass on the x position and the mass on the y position. It is also important to note that in this case, our zero position would be at the top of the pendulum, so the positions of our pendulum are gonna be in the negative y-axis. Here is a close-up of the graphs that we got from Tracker. As you can see, the top one tracks the position of the x, and the second graph on the bottom tracks the position of the y. As you can see, both of these oscillate between up and down, showcasing an oscillation between both the x and the y axis. So now moving on to our experimental code, we had to edit some parts of the code. In this case, the first part was to update the mass of our ball. In this case, it was set to 0.5, and we also updated the initial position of our ball. Now for the calculation loop, we had to do a series of updates. So for the first part, we had to define our initial energies, which you can see there accordingly. The next part was to calculate the gravitational force, which I started by doing by updating the ball mass with the gravitation. Then we had to calculate the spring force and mass by spring, followed by the net force, followed by the momentum principle update, in which we update the object's velocity and the position. Then we also had to update the spring, and finally we just had to calculate the energy changes. We did all of these by making use of the formulas that we showcased at the beginning of the experiment. Finally, here are our experiment model results. As you can see, the mass of our pendulum moves in a slower manner than it did in our original video. This might be due to some miscalculation on the masses or initial velocities. But overall, I think it's a pretty accurate depiction of the movement despite of the movement time. Now, to conclude our lab, what does this mean? For your model system, is the energy principle satisfied? The answer is yes, the energy principle is satisfied because overall it does state that the energy is conserved, and in this case, the total energy is zero. And to answer the second question, we can hypothesize that the differences that are there may be caused because we might not be taking into account drag force, or there might be some inconsistencies when making use of tracker and tracking the mass.